Okay, so welcome to Fourier series. This is day 2. My name is Sujit. If this is your first day in class, please read the syllabus carefully. It's posted on canvas.colorado.edu. The main thing is we have a homework pretty much due every week. We have 2 exams, and then there's a group project at the end of the semester. So I'll let you take a look at the calendar, and we'll talk about that stuff as we get closer to it. So Canvas is our main source of information, a dispersal. That's where I'll put all the happenings on Canvas. So last time we talked about the syllabus. We, motivated why we want to study PDEs. And then we talked a little bit about the idea of mathematical modeling. At least the type of modeling we're doing here is a physics-based modeling that yields mathematical equations as models. There's many other types of modeling. And we also discussed some of the objectives of the course, mainly being that, in this class, we're going to study some very important fundamental PDEs. This is not a PDEs class in the sense that we try to solve every PDE that ever existed. No differential equations classes like that. So we'll study some, classic canonical fundamental PDEs like Laplace's equation, the heat equation, the wave equation, and try and solve those, because these are really fundamental. And so one thing I mentioned is in this class, you actually won't learn any new math. You already know all of the actual math that you need. What we'll do is we'll now take all of this math that you've learned from all these different classes like Calc 1, Calc 2, Calc 3, matrix methods, differential equations, and we'll put it all together now. And so what students sometimes find is tricky is they don't remember their sequence and series from Calc 2. They don't remember the Fubini's theorem from Calc 3. So it's those little things you kind of have to review and stuff like that. So anyway, part of my goal today is just to warm you up, get you reviewed up, and then we'll start doing homework and stuff, and we'll start doing Fourier series. So the idea with Fourier series is, first of all, it's a series. It's very important that you say, first of all, we're dealing with an infinite sum. So anytime you're dealing with an infinite sum, we have to at least address the issue of convergence. Fourier himself did not address the issue of convergence. Fourier just solved PDEs and tried to do whatever they could with it. But we'll go into the mathematical theory. And so the first couple of lectures, first couple of weeks in this class is devoted to that mathematical theory. So we won't even solve a PDE until week 4. So I think it's really important to keep that in mind. We're getting kind of the dry analysis out of the way at the beginning, and then we'll start solving PDEs and things will get, much more exciting. So here I have a graph of the cosine and sine function from minus pi to pi. Typically we look at these functions from 0 to 2 pi, but in this class, this is how we want to look at these 2 functions from minus pi to pi. And the cosine and sine function will be the basic building blocks with which we will create a Fourier series. And then we'll use the Fourier series, we'll try and then pose a solution to the PDE that utilizes aspects of the Fourier series. So I want to remind you, so now we're going to be working with sine and cosine a lot. So I want to remind you that we have some of these trig identities, which are called the sum and difference identities. And for us, the main use of these sum and difference identities is we can come up with identities for the, for products, for these product formulas. So here for this first formula, let's just think about how do we get it? It's not difficult. If we add these 2 equations here, if I add the top equation to the bottom equation, these terms cancel, these terms double up, and these terms add. We've added these 2. So if I divide by 2, I get sine alpha cosine beta equals sine of alpha plus beta plus sine of alpha minus beta divided by 2. And how is this useful? So what we're going to be doing is a lot of integration. Okay, so this is useful if I now want to integrate sine of alpha times cosine of beta. I can use the identity, replace it with this average here of sine of alpha plus beta, and sine of alpha minus beta, and integrate the expression on the right-hand side, which is much easier to work with in terms of integration. Okay. And so similarly, these other two formulas you can get by adding these two, and then some of them you can get by subtracting. Okay, so this one is a subtraction. And so terms cancel out and you divide by 2, and then so you get a formula. And so yeah, for both of these formulas, we'll make integration much easier. And why are we integrating? I'll tell you why we're integrating shortly. Maybe by Friday we'll get to it. So there's a bigger picture here, and what we're just kind of trying to put the tools in place first, so that when I show you the math, you're not like, wait, what did you do? So I want to first show you the identities we're going to use. I want to show you the math technique we're going to use first, and then start doing the theory. So I wanted to do a little math problem here as a warm-up. This also gives me an opportunity to talk about two very important concepts in math. Number one being the absolute value, and number two being the triangle inequality. So, triangle inequality is very important for doing analysis. So here, first of all, just want to remind you the definition of the absolute value. So the absolute value of A is defined to be, so here we're looking at the thing in between the vertical bars. If the thing in between the vertical bars is greater than or equal to 0, then we just spit out whatever's in between the vertical bars. If the thing in between the vertical bars is less than 0, then the function spits out negative of whatever's in between the vertical bars. And you remember how the absolute value function works. Calc 1 wasn't that long ago, was it? And of course, the absolute value function is always non-negative. And now a very important fact about the absolute value is that a number or the negative of a number is always less than or equal to its own absolute value. So let's think about this. Let's just quickly think about this, and we'll do this by cases. The trick here is to do this by cases. So here, suppose A is positive. If A is positive, then the absolute value of A is just A, and then you'll have equality. This is if A is positive. So yeah, A will be greater than or equal to A. If A is positive and you put a minus sign in front of it, then it's negative. So certainly that'll be less than the absolute value of A, because the absolute value of A is always greater than or equal to 0. So that's if A is positive. If A is negative, then the absolute value here, this will be, remember, A will be a negative number. The absolute value here will be minus A, but be careful. Minus A is actually a positive number if A is negative. So minus A will be bigger than A, because minus A will be positive and A is negative. And that if you multiply both sides by a negative, the inequality still holds. So here, a number or its negative is always less than its own absolute value. And so now we can prove there's many ways to prove the triangle inequality. This is just one way to do it. I just do it by cases. I just assume if the thing in between the vertical bars, if A plus B is positive, then the absolute value of A plus B is just A plus B. Now A is less than the absolute value of A, less than or equal to, and B is less than or equal to the absolute value of B. And so we've got triangle inequality. That's case one. If A plus B is negative, which is the only other possibility for real numbers, right? So here, if this is negative, then the absolute value spits out, negative quantity A plus B. So that this will be a positive number. So now distribute the minus sign, you get this is minus A plus minus B, but a number or its negative is always less than or equal to its absolute value. So we're back to triangle inequality. So I've proved it in every possible case for A plus B. I've proved it if A plus B is greater than or equal to 0, and I've proved it if A plus B is less than 0, And those are the only two possibilities. In both cases, I ended up with the same conclusion. In both cases, I got the same conclusion, right? Regardless of whether a plus b is greater than or equal to 0, or if a plus b is less than 0, we end up with the same conclusion. So it's proven outright as a, so for any real number, this is now always true. Triangle inequality is always true. And so we'll use triangle inequality. Triangle inequality is super important in analysis. If you're taking analysis class, triangle inequality. One thing is all of our math up until this point, is typically focused on using equalities. And so now when you do analysis, everything is involving inequalities. So we kind of have to build this new toolkit of how do we work with inequalities. And so triangle inequality is the first and most fundamental tool here. So let me remind you, and this will seem random. It's like, why are we just talking about random math topics? We will use everything that we're talking about today. So let me remind you of the hyperbolic functions. When we are solving Laplace's equation, which is a PDE, the hyperbolic functions will appear. They will be used to characterize a part of the solution. So now a hyperbolic function is much more complicated than it sounds. We define cosh and sinh using the exponential functions e to the x and e to the minus x. If we add e to the x to e to the minus x and then average, we call that cosh, the hyperbolic cosine. And if we do e to the x minus e to the minus x and divide by 2, here we're averaging e to the x and negative e to the minus x. If you average those two functions, we call that function sinh. So why do we create these functions? Because it shows up a lot. It shows up a lot in PDEs. Because this expression kept showing up so much in PDEs, we gave it a special name so that we didn't have to write e to the x plus e to the minus x over 2 every time. We just write cosh x. And similarly for sinh. I'll show you, when we solve the PDEs, these expressions, these linear combinations involving e to the x and e to the minus x are very natural. We will see when we do separation of variables and start solving PDEs. So just some identities that are, very easy to prove if you go back to the original definition. Cosh plus sinh equals e to the x. So right now, just go back to the original definition. I'm just adding e to the x plus e to the minus x over 2. And I'm adding that to e to the x minus e to the minus x over 2. So here, the e to the minus x cancels out. And the e to the x doubles up. So I get 2 e to the x over 2, and the 2's cancel out. And similarly, you can show cosh minus sinh is e to the minus x. If you multiply these two, if I now multiply these two equations, multiply cosh plus sinh to cosh minus sinh, I'm going to get cosh squared minus sinh squared. And on the other side, I'm multiplying e to the x to e to the minus x, which is giving me 1. And so this identity, so with regular trig, we have cosine squared plus sine squared equal to 1. With hyperbolic functions, we have cosh squared minus sinh squared equals 1. And by the way, this identity is why we call the functions hyperbolic. So the difference of 2 squares equal to 1. So if you look at the graph of x squared minus y squared equal to 1, for example, the graph of this is a hyperbola. The graph is a hyperbola. And so that's why we that's why we call these functions hyperbolic. Simply because of this identity. There's no other reason. That we have a difference of squares equals 1. And in geometry, when we have a difference of spatial variables, the square of spatial variables equal to 1, the graph of that is a hyperbola. So we call these hyperbolic functions. That's the only reason, and it's a very complicated name, but unnecessarily so. We should not let the terminology, at all mess with us. So we have I'll show you the graph here. So we can graph these functions because we know the graphs of e to the x and e to the minus x. So it turns out the hyperbolic cosine is an even function. and the hyperbolic sign is an odd function. I'll show you the graph here in 1 second. And here we also have some sum and difference identities. You don't need to memorize these. You just need to be aware of them. And you just need to remember that they exist when we're going and solving PDEs. When I use a hyperbolic identity, you just have to be like, oh, okay, he's just using one of those hyperbolic identities. You don't need to actually memorize it. You just need to be aware and remember the math and remember how we work with these functions. And so for the hyperbolic cosine, we also have a sum and difference identity. So the hyperbolic functions we won't use for quite a while, but anyway, here are the graphs. I've graphed each one of them. You can say sinh is an odd function. Cosh is an even function. It's bounded below by 1. So cosh is even and positive. And tanh has horizontal asymptotes at -1 and 1. The hyperbolic tangent graph looks very similar to the arctangent graph. So it might look similar to you, but so arctangent goes between -π/2 to π/2, and this hyperbolic tangent just happens to look similar, goes between -1 and 1. So we will come back to hyperbolic functions much later in the semester. This is just, and of course you can always come back to these slides if you want to go, wait, how did that go again? So they're here for you to, just remind yourself of this math that we studied in Calc 1. So these functions are typically introduced in Calc 1 or earlier, depending on, the curriculum. Okay, so that was a little Calc 1. Little Calc 1 warm up with the hyperbolic functions, even functions, odd functions, cosine and sine. So now I want to review sequences and series from Calc 2. So remember that a Fourier series is first and foremost a series, right? So a sequence, so let me go backward one more step. A Fourier series is a series. And now remember, a series is actually a special type of sequence. So let me talk about what a sequence is, and then let me use sequences to define series, and then eventually we'll talk about a Fourier series. Okay. So a sequence, as you remember, is a countably infinite list of numbers, a sub n. So we have a sub 0, a sub 1, a sub 2, just your counting numbers 1, 2, 3, 4, 5, 6. That's a sequence, right? Your stock prices that come in, that's the sequence of numbers. So a sequence is an infinite list of numbers. And what we're interested in is, what's the long-term behavior of this list of numbers? Are these list of numbers approaching one number? Or are they going all over the place? Or are they getting bigger and bigger, smaller and smaller? So if the infinite list of numbers is approaching one single number, getting closer and closer to one number, for example, if I have 0.9, 0.99, 0.999, 0.999, isn't it hilarious when I try to write 0.9999? You can see this sequence would be approaching 1. It doesn't ever get there, but it gets infinitely close to 1. 0.9, 0.99, 0.9999, So that's a sequence that's converging to 1. So we say a sequence converges if and only if the limit of a sub n as n goes to n infinity equals capital L, where L is a finite number. That's really the most important thing here, that convergence means the sequence is approaching a fixed finite number. And I did a cheesy example here. I'm looking at 2 to the minus n, so that's 1 over 2 to the n. Right, so when n is 1, we have a half. When n is 2, I have 1/4. When n is 3, I have 1/8. That's all. That's as high as I can count. It was 1/16, 1 over 32, 1 over 64, right? So as n goes to infinity, this sequence will approach 0. If you agree with me, say nothing at all. Okay, great. Zoom, teaching on Zoom, what I mean. So yeah, convergence of a sequence, okay, an infinite list of numbers. Now, a little bit tricky. Let's bump up to a series. A series is a type of sequence. Okay, so first of all, a series on its face value looks like an infinite sum. So we use sigma notation. This says this is sigma n going from 0 to infinity of a sub n. So this is, you know, notation for a sub 0 plus a sub 1 plus a sub 2 plus dot dot dot. I'm okay with the first three terms. It's the dot 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 that worries me, right? So we should be very careful and don't just think of this as a sum. We should think of this as a sequence of partial sums. So we should think of this as the sequence where the first term, whoops, sorry, so the first term of our sequence is a sub 0. Then the second term of our sequence is a sub 0 plus a sub 1. And the third term of our sequence, or of our series, which is a special type of sequence, it's a sequence of partial sums. So these things that I'm writing here are the partial sums. So the third term of this infinite series, which is actually a sequence of partial sums, would be a sub 0 plus a sub 1. There should be a 2. I skipped 2, people. A sub 0 plus a sub 1 plus a sub 2, so on and so forth. Okay, so we're really looking at the series. I think of it as an accordion, like that you're expanding. So I first look at a sub 0, then I look at a sub 0 plus a sub 1, then I think about a sub 0 plus a sub 1 plus a sub 2, and I think of it as kind of an accordion, expanding from the center, ever reaching out. And then we're thinking about what's happening to these individual partial sums. Are they slowly approaching one single number? So that's the idea behind a series. And it's, it's weird because it's a sum, but it's really a sequence. It's really, a sequence of finite sums becomes this thing we call an infinite sum or a series. So yeah, the nth partial sum, as I was talking about, is just defined to be the sum of the first, in this case, n plus 1 terms. So remember here, you have n plus 1 terms because we're starting at 0. And if this sequence of partial sums converges, then the series is set to converge. So here I say, the series converges to L if and only if, so this is defining what it means for the series to converge, if and only if this sequence of partial sums goes to L, where L is some fixed number. So here, remember what we're doing, it's like an accordion. I'm looking at a sub 0, then I'm looking at a sub 0 plus a sub 1, then I'm looking at a sub 0 plus a sub 1 plus a sub 2, and I'm looking at that sequence of partial sums and asking what's the sequence doing. Whatever the sequence of partial sums does, that's what the infinite series by definition must do. So the sequence of partial sums and the infinite series are the same thing. So if a series or sequence does not converge, it is said to diverge. Remember, there are multiple ways to diverge. Something could blow up to infinity. Something could go down to negative infinity, or a sum or sequence could oscillate forever between two numbers. So there's more than one way to diverge. There's only one way to converge. So now, if you're doing okay, we're going to take it up one more notch. And so when we talk about convergence of a series, specifically a series, there's two types of convergence. There's what we call conditional convergence and absolute convergence. So now this is about the difference between the original series here. We've got the original series. We want to compare that to the series of the absolute value of the terms of the original series. So that's really important here, that, and so one thing to mention immediately, if you have a series of positive terms, then there's no difference and there's only two possibilities. If you're looking at a positive series, then it's either divergent or absolutely convergent. So this conditionally convergent business only makes sense if you're dealing with a series that has non-negative terms, positive and non-negative terms, a mix of terms, essentially. We typically find conditional convergence for alternating series. So what's the definition of conditional convergence? I give you the definition here. We say a series is conditionally convergent, okay? If and only if the original series converges, but the series of absolute values diverges. So here the series of absolute value does not converge. So the original series converges, but if you take the series and take absolute values and just add them all up, that blows up. So then that's called conditionally convergent. And we contrast that with absolute convergence. This is when the series of the absolute value of the original terms converge. And I'll show you in a second when that happens, that'll force the series of the original terms to converge. In this case, both of these associated series, the original series and the series of the absolute value of the terms, both converge. This is called absolutely convergent. Absolutely in the sense of the absolute value, right? So I want to just pause for a second. You know, I don't know when the last time you did sequences in series were. I live it every day, right? So for me, it's like, yeah, conditionally convergent, you know. So yeah, you know, at the end of the day, it's important to think about the series and the series of the absolute value of its terms. That's really what this game is about, and which are converging and which are not. And so I want to remind you now, what we have from Calc 2 is a bunch of tests and various criterion which we can use to determine whether a series is converging or diverging. Like some of your favorite tests that you know and love. Remember ratio tests? Oh yeah, good times. Root test? Oh yeah, direct comparison test. So let's review some of those series tests that you've missed, because they're like, you know, good friends that we haven't seen in a long time. Maybe, I don't know, maybe you're doing series all the time. I am. So the divergence test, this is the most fundamental and basic test. The divergence test, first of all, is a test for divergence only. Remember the mistake all the students make in Calc 2 is try to use divergence tests to conclude convergence, right? So divergence test, first of all, when it works, will only tell you something diverges. So it says, if the limit as n goes to infinity of our series terms does not go to 0, then the series has to diverge. You know, it's logical to think about if I'm adding an infinitely many number of numbers, the only way that's not gonna keep growing is if the numbers I'm adding get smaller and smaller. I mean, ultimately, I'd expect the numbers have to go to 0 so that the infinite sum would actually add up. Otherwise, it'll keep accumulating value if the actual numbers we're adding to it weren't getting smaller. So that's basically what the divergence test is saying, that if the numbers we're adding aren't getting smaller, if they're not approaching 0, then there's no way the series can diverge, because we're always going to add numbers that are going to, you know, contribute to the overall value. And the series is going to do something. Either it's going to grow or get smaller if you're adding negative terms. Either way, it's not going to converge. So this is the most fundamental test. This is pretty much the first test we always kind of mentally check when you're giving a series. You know, if I send n to infinity, does a sub n go to 0? Now, if a sub n does go to 0, that's not a guarantee of convergence. That's where most students make the mistake. They say, oh, well, then this means that if the limit of a sub n is 0, then the series converges. And that's not logically true. That's not logically equivalent. What is logically equivalent is if we know the series converges, then we know the limit of a sub n goes to 0. But if we know the limit of a sub n goes to 0, that doesn't tell us the series converges. This is, you know, this subtlety of the logic that it's not a biconditional statement. It doesn't go both ways. a geometric series is the next most fundamental series, and we'll do a lot of geometric series stuff in this class. We'll also do a lot of ratio test, root test kind of stuff. So geoseries, remind you of the form of it. This is one way to write a geoseries. It's sigma n going from 0 to infinity, a times r to the n. What you should do is think about what the actual sum looks like, not the sigma notation. So I want you to, in your mind, if you write this out, this is a plus ar plus ar squared. This is what I want you to think of as a geometric series. Remember, the notation, the series notation is just, a way of representing the series. It's not the actual series. We really want to write it out. And that's what I think of as a geometric series, where each term, the next term is multiplied by r, right? You start with a and then multiply it by r, so you get ar. Then the next term, you take ar, multiply by r, you get ar squared. Then for the next term, you take ar squared, multiply by r, you get ar cubed, so on and so forth. So this is a geometric series. And I'll show you the proof in a second here, but here's the result that's really important. If r is less than 1, sorry, I was still on black. If r is less than 1, then the series will converge. And in the case of the geometric series, not only can we tell you that it will converge, we can tell you what it adds up to, which is really a great result. And I'll prove this to you in a second. At the end of the day, you just need to know the result. Especially when I use it, you shouldn't be like, wait, what did you do? That's geoseries. And if r is greater than or equal to 1, the geoseries will diverge. So let me prove this result. It's not hard. And this will be good just to warm our brains up. So here, I'm looking at the sum of the first n terms. So I don't know if I'm a little bit inconsistent with my partial sum, but it really doesn't matter. I'm looking at the sum of the first n terms. So here, this starts with, this is my first term, my second term, my third term, and this will be the nth term. Okay, so I've got the sum of the first n terms. Now, the trick, and this is to use the similarity here. The trick now is to multiply both sides by r. Multiply both sides of the equation by r. And so I've done that below. I multiplied both sides by r. So then here, this term becomes ar because I multiplied by r. This becomes ar squared. This becomes ar cubed. This becomes ar to the n minus 1. This becomes ar to the n. You multiply all through by r. Now comes the trickery. We're going to multiply the bottom equation by a minus sign and then add top and bottom. So I'm doing s sub n minus s sub n times r. I'm subtracting the bottom equation from the top equation. Okay, I'm doing top minus the bottom. So look what happens. Here, this ar, whoops, let me do this. This ar right here will cancel with this ar. This ar squared will cancel with this ar squared. This will cancel here. This will cancel here, this will cancel. The only terms that survive are the first term a and the last term a times r to the capital N. So subtract the bottom, subtract the bottom from the top. Everything in between cancels out. We're only left with the first minus the last because we're subtracting. And now here, factor out the a. Here, factor out the s sub n. So this is s sub capital N times 1 minus r. And divide both sides. I want to isolate the s sub capital N. I'm trying to find the limit of the partial sums. Remember, a series is basically the limit of its partial sums. So here I'm trying to find a closed form expression for the partial sum so I can take the limit of the partial sum and figure out what the series is doing. So if I divide by 1 minus little r at the bottom, I've got s sub n now will be isolated, right? We'll just have S sub n over here. So when I do that, I get, here's my formula. Now we can send capital N to infinity. And look, the only term that has a capital N on it is this term in the numerator. So the behavior of the partial sums all depends on the behavior of that numerator term. If that numerator term is greater than 1, a number greater than 1 raised to n, and you send n to infinity, that's going to blow up. If that number r is less than 1, like if its absolute value is less than 1, so if it's in between -1 and 1, if it's, you know, a fraction, 1 over a number larger than 1, if it's a fraction, when you raise it to n and send it into infinity, that's going to shut down to 0. And the partial sum will go to a over 1 minus r. So here, when we take the limit of the partial sum, the limit will only exist if the r is in between -1 and 1. If r is not in between -1 and 1, this term will blow up to infinity. If r is, you know, bigger than 1 or less than -1. But if r is a number between -1 and 1, that's like, you know, a fraction, like 0.2 to the n, you're making it bigger and bigger, the denominator is blowing up, the fraction shuts down to 0. So, and remember, the limit of the partial sums and the series are the same. So this is actually what the series is equal to. So yeah, you should, you know, just remind yourself of the details of geoseries and be aware of this result. You don't need to know the proof that I just did. I just wanted to do the proof for you because I didn't want to give you the formula without justifying it. You know, so now you, at least you kind of, just to warm you up from Calc 2, it's been a while, you know. All right, here's another test, the direct comparison test, which we'll use a lot. So this says, this is for non-negative series. First of all, that part's really important. Okay, we only use direct comparison test on non-negative series. So that's why it starts out saying, assume here a sub n is non-negative, b sub n is non-negative, and a sub n is less than or equal to b sub n. And so then we immediately get a conclusion. Then I can immediately conclude the series a sub n, n going from 0 to infinity, is less than or equal to the series a sub n, n going to, b sub n, n going from 0 to infinity. And they're both non-negative. So basically the way I think about it is, for this inequality, we just slapped on some sigma notations. And you get this equation. That's how I think about it in my mind. Just from here to here, we just slapped on some sigmas. Okay. So now here's the result. Using this inequality, if I know sigma b sub n, let me use a different color. If I know sigma b sub n converges, is equal to some finite number, let's say this is equal to 3, then I know this series is between 0 and 3, and since it's a series of non-negative numbers, we're only adding numbers that are non-negative, that series has to converge. It can't oscillate. The series here can't go between, you know, you can't oscillate up and down between some number that's between 0 and 3, because we're adding positive numbers. Since we're constantly adding positive numbers, the only thing that series can do is either get bigger and bigger or converge. And here I'm showing the direct comparison test shows if sigma b sub n is converging, then the series is not growing. And if this series of non-negative terms is not growing, then it's converging. So that's one conclusion that I've got here. Sigma a sub n converges if the b sub n converges. So if, whoops, what happened there? If b sub n converges here, right up here, if b sub n converges, then we get a sub n converges. And the other result we can get from this situation of this inequality right here is if this series here, sigma a sub n goes to plus infinity. Remember that series can only converge or go to plus infinity because it's a series of non-negative terms. If this goes to plus infinity, then the only way this equality makes sense, the only way sigma b sub n is, greater than or equal to sigma a sub n is if it also blows up to plus infinity. So the other conclusion we can get from direct comparison test is if sigma a sub n diverges, then sigma b sub n will have to also diverge. Remember, sigma b sub n can only go to plus infinity or converge because it's a sum of non-negative terms. Here we're showing it's not possible for it to sum to a finite number because it's greater than something that's blowing up to infinity. So the only way that makes sense is if it itself is blowing up to infinity. Direct comparison test. It's a beautiful thing, and we will use it. And for you, just to remind you of direct comparison test, if you haven't seen it in a while. All right, so I do an example here using the direct comparison test, and I want to prove this very important result. That given a series, if the series of the absolute value of the terms converges, then we know automatically the original series will also converge. And in this case, the series is absolutely convergent. The original series is absolutely convergent. So is the series of the absolute values. So this is an important result that you should know that we'll use, and let me prove it for you. And I'll prove it using a direct comparison test. Okay, so here's some analysis for you. So we start with this inequality. So first, just focus on this inequality and don't look at anything else. So here, focus on the middle. Start with a sub n plus the absolute value of a sub n. Now we know a sub n will be less than or equal to the absolute value of n. And then I've got another absolute value of n here. So that's, I can just copy that down. So I get a sub n plus the absolute value of a sub n would be less than or equal to 2 times the absolute value of a sub n. Remember, a number is always less than or equal to its absolute value. A number or the negative of that number is always less than or equal to its own absolute value. So now, why did we do this? Because here I'm not assuming necessarily that a sub n is non-negative. Here, a sub n could be negative, okay? Not necessarily positive. So here, maybe can I try this? Here, this is not necessarily positive, or let me say non-negative. So that's one thing I should mention, because if you're even like, what's the problem? Just say a sub n is less than the sigma of absolute value of a sub n and we're done. Well, we can't use direct comparison test because I'm not assuming we're starting out with a non-negative series. So the thing about a sub n plus a sub n, this is always going to be greater than or equal to 0. If a sub n is positive, then obviously a sub n plus the absolute value of a sub n will be greater than 0. If a sub n is negative, this will be a sub n plus, if a sub n is negative, the absolute value here will be negative a sub n. So I know for sure this expression is always non-negative. That's why we're doing this trickery, first of all. So first and foremost, understand why we're even doing this trickery. Because I'm not assuming that a sub n is non-negative. I'm assuming a sub n, could be anything, any real number. So this is always mathematically true. The a sub n plus absolute value of a sub n will be greater than or equal to 0 and less than 2 times the absolute value of a sub n. And now I can use direct comparison test. So now slap on sigmas here and here. And so we end up here. And now in the theorem, in the example, we're allowed to assume that this series of the absolute values converges. That's the hypothesis here of the example. In the example, where it says if so we're allowed to assume that this series converges. That's something we're given. So I know, this series here. So if a series converges, then 2 times that series will also converge. Okay, I won't prove that. I'll just let you think about it from Calc 2. You can prove it, using a thing called proof by contradiction. But basically, if this adds up to a number, then we multiply it by 2, that'll still add up to a number times 2. Okay, so that series converges. So direct comparison test then tells us the series in the middle will converge. So here I kind of discussed this a little bit. So if we assume the series of absolute value converges to some number L, then if you multiply by 2, it'll also converge. It'll converge to 2L. So by direct comparison test, the series in the middle here has to converge by direct comparison test. So last step, we now know from Calc 2 that the difference of 2 convergent series is once again convergent. So here we take this series that we've proven to be convergent and we subtract it from the series that were given to be convergent. And what we get is just the series of original terms. And since it's a different of 2 convergent series, it itself is convergent. So if this seems a little weird to you, there's some subtle analysis going on here, that has to do with how series behave. And this is certainly, I would say this is a little bit on the deep side, if you're not used to sequences in series. So it's okay, just take it slow and go back and review, concepts of sequence and series and go back and look at this example and, make sure you understand why I'm solving it the way I am solving it, why I did this very first trick up here. Why was that even necessary? So, yeah, so it is true. So this is a true statement that the absolute value of the series is less than or equal to the series of absolute values. That is a true statement. And you can use that to prove the result we proved here, but it's not quite as simple as one might think. The actual proof is a little bit tricky. And so here I'm getting a little bit technical. For those of you in analysis, this might be of some minor interest to you. The rest of you, this is really not that important. But yeah, so to use this result here to prove this result up here, we need a thing called a Cauchy criterion. And since this isn't a proper analysis class, as a Fourier series class, I'm not going to go into it. But yeah, some students always ask me, hey, can't we just use the fact that the absolute value of sigma a sub n being less than the sigma absolute value, can't we just use that? Doesn't that immediately imply absolute convergence? And the answer is yes and no. It doesn't immediately imply absolute convergence, but you can use it as a starting point, but more analysis is required to actually formally prove the result. Okay, well, I'm not going to go into it because I seem to be worried about this probably more than anyone else is. But at the end of the day, the result we must know is this one up here, that if the series of absolute values converges, then the original series also converges. And in this case, the original series is absolutely convergent. The series of absolute values also is absolutely convergent. So that's really the important. We'll use this result a lot of times. Rather than trying to work with the original series, we'll look at the series of absolute values and it'll be easier to work with, and we'll be able to show it converges, and then we'll immediately from this result get that the original series converges. Okay, so that's kind of how we're going to use this result. Frequently it's easier to work with the series of the absolute value, like you're dealing with sine and cosine. Of course, I want to hit it with an absolute value because I know the absolute value of sine is less than 1. I know the absolute value of cosine is less than 1. I can start to use those types of inequalities to maybe do some analysis, do some math. So that's how we'll use that a lot. Okay, so, here we go. So let me talk about rearrangements. This goes to the analysis of Fourier series. Okay, this goes to why, when we do all this analysis, you're going to ask the question, who cares? Why do we have to worry about the convergence? What's the problem? Can't we just do the math? What's the big deal? So this is kind of part of what the issues could be. Okay, so here's the issue. So you know that the order that which we add numbers doesn't matter. A plus B equals B plus A. Actually, that's not true. That's only true for finite sums. For infinite sums, the order in which we add the numbers does matter. Okay, especially if you're dealing with a conditionally convergent series. So suppose we're given a series, some series, n going from 1 to infinity with partial sums s of n. So what I want to do now is create a new series. I'm going to pick terms randomly and add them. So here I randomly picked A66 to be the first one. Then I picked A sub 879 to be the second one. Is it past time? What time do we end? Oh, God damn it. I thought we ended at 11:20. My bad, y'all. Thank you for someone saying something. I'm going to stop right here. You know, my problem is I'll just talk forever about it.